AP Chemistry Periodic Table, Ionization Energy. Specifically, what we're going to be looking at today is definition of ionization energy, first, second, third ionization energies, ionization energy periodic trends, and anomalies in ionization energies. So let's talk about ionization energy. The first ionization energy, which we represent as an I with a little sub 1 of an atom. That's defined as the energy required to remove the outermost electron from the ground state of a gaseous atom. Ionization energy is always positive because removing an electron always takes energy. This would be considered an endothermic reaction. You must put energy in to remove one of these electrons. So for example, the first ionization energy for magnesium is 738 kilojoules per mole. The second ionization energy, or I with a little sub 2 of an atom, is the energy needed to remove the second electron. So for example, the second ionization energy of magnesium is 1,451 kilojoules per mole. For all atoms, the first ionization energy is going to be less than the second ionization energy, which is going to be less than the third ionization energy, because with each successive removal, an electron is pulled away from an increasingly more positive ion. So if we look at this table below, we can see for sodium, the first ionization energy is 496 kilojoules per mole. But once we go beyond that one valence electron into the second ionization energy, we see a huge jump because all of the sudden we are in our core electrons. Same thing for aluminum. We know that aluminum has 3 valence electrons. So the first ionization energy is 578. The second is 1,820, so a little bit higher. The third one is 2,750. But the fourth one, again, once you get into those core electrons, the amount of energy needed to remove a core electron is much higher than one of the valence electrons. Ionization energy trends across a period. First ionization energy in general increases from left to right across a period. This is primarily because we go from our metals, like in group 1 and group 2. They release their electrons very easily because they want to look like the closest noble gas. We see an increase in ionization energy as we go through the transition metals, and then definitely through groups 13 through 17, high ionization energies because they would much rather gain an electron to get our full octet rather than lose them, so they're more apt to hold on to their valence electrons. Anomalies in ionization energies occur between groups 2 and 13 and groups 15 and 16. Electrons in filled s or d orbitals provide limited screening for electrons in the p subshell. Those electrons in the p subshell are more vulnerable to be removed and require less energy than would be predicted. So if we looked at the electron configuration for sodium, we know that the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. It's not a surprise that this one electron in this s sublevel is pretty easily removed. But when you go to magnesium, the electron configuration is 1s2, 2s2, 2p6, 3s2. Now we have that filled orbital for that s sublevel. It's going to be difficult to remove an electron from that filled orbital. Now, one might predict that aluminum would have a higher ionization energy, but that's not the case. So let's look at the electron configuration for aluminum, and that is going to be 1s2, 2s2, 2p6, 3s2, 3p1. And this one electron in this p subshell is easily removed because this 3s2, the 2 electrons in this 3s sublevel, are going to have limited shielding, which makes this particular electron pretty vulnerable. Even though the general trend is that as you go across a period, the ionization energies are going to increase. Now you might be asking, well, what about the difference between nitrogen and oxygen? again, one would predict that as you go across the period, the ionization energy should increase. Let's look at the electron configuration for sodium. That's going to be 1s2, 2s2, 2p3. Now, the important thing to notice here is that in this particular sublevel, we have 3 electrons. So if I draw my little boxes here, I could say, all right, I've got 3 electrons, 1, 2, 3. And that's a pretty stable configuration. But when you go to oxygen, the electron configuration is 1s2, 2s2, 2p4. So now if I draw my boxes out like so, we're going to have 1, 2, 3, 4. And right here, in this box right here, representing those 2 electrons, because there's 2 electrons in that orbital, there's going to be repulsion. And because there is repulsion, it's going to be easier to remove one of those electrons other than the stable electrons all with the same spin. Ionization energy trends down a group. First ionization energy will decrease going down a group. And we can see it here by looking at some group 1 elements. Lithium is 520, sodium is 496, potassium is 419, and rubidium is 403. Because as those electrons get farther and farther away from the nucleus has less of a hold on those valence electrons, and it's easier to remove them. Examining changes in ionization energy within an atom. Aluminum has a first ionization energy of 578, a second of 1,817, a third of 2,745, and a fourth of 11,577. So you could say to yourself, wow, there's a pretty big jump between these 3 ionization energies and this 4th one. Because remember, these 3 ionization energy represent our 3 valence electrons. So you can pretty much predict how many valence electrons an element is going to have just by looking at ionization energies. As soon as you see a relatively big jump, at that point you know that you've gotten into your core electrons. So what did you learn? We looked at the definition of ionization energy. We talked about the difference between a first, second, and third ionization energy. We looked at some ionization energy periodic trends, and then finally some anomalies in ionization energies. Need more help? Feel free to contact me. Have a great day.